Okay, so today I'm going to be reviewing a little bit out of the quadratic relation. Whole purpose of this is to try to make the quadratic unit more understandable. There's a lot of material to cover, and the quadratic unit in Math 10 is usually really intense, and it is very dense, and there's a lot of information. So I'm going to try to walk you through the quadratic relation right now. First couple of things, obviously, when you're plotting a quadratic, you end up plotting a shape called a parabola. Okay, so it's usually either facing down, so this is facing down, or facing up. And what it means is that it opens, the opening is facing upward, right? So there's an opening here, and it's facing up, and over here the opening is facing down. Okay, so these two guys, these two guys are both parabolas. This is the name for the shape that you end up plotting. So the parabolas, I have to plot these guys, and generally I'm going to ask you to plot a parabola given some quadratic equation. Now, there was a quadratic equation form or relation form that we talked about. The form is standard form. Okay, so there are multiple ways, so I'm going to write this. There are multiple ways to write a quadratic equation or quadratic relation. That is to say, there are multiple forms. Oops. So, the first way is, as I said, standard form. So it's y equals ax squared plus bx plus c. So this guy is called standard form. Then there is another form called vertex form. But these two guys represent the same type of curve. It's still a parabola. They're just written in different forms. That's it. So it's not a different concept, it's just they both represent the parabola, and it's just written in different ways. Now, so we're going to start in general terms, talking about a quadratic relation. There's some things that we need to know. So in a quadratic relation, I'm just going to draw a very random, that's not a very good parabola. I'm just going to redraw this. Hopefully that's a better parabola-ish. Okay, this is a very random parabola, but I'm going to label some things on it. Okay, this guy at the end here is called the vertex. Okay, now if I drew it upside down, if I drew a downward facing parabola, this guy would also be the vertex. It's at that same point in the middle. Whoops, in the middle. Supposed to be through the vertex. We call this line the axis of symmetry. Axis of symmetry. The axis of symmetry has an equation of x equal to blah blah blah, some number. Okay, this number is the x coordinate of the vertex. So for example, if the vertex of a parabola is, say, 2, 3, then this means the axis of symmetry is x equal to 2. I take the x-coordinate of the vertex, punch it in, and I get the axis of symmetry. Okay, so the axis of symmetry is always x equal to a number. Moreover, okay, I can plot a curve, a parabola. Okay, and the axis doesn't line up really nicely, but let's say I plot this curve. So start at 0, 0. That's the vertex. Move over 1 to the right, move up 1. 1 to the left, move up 1. 2 to the right, up 4. 2 to the left, up 4. Okay, oops. Terrible line. Almost. It's really hard to do this on a graphics tablet. Okay. This guy is going to have an equation y equals x squared. So the axis of symmetry is going to be right down the middle, okay? And the vertex coordinates here are 0, 0. Okay. So the axis of symmetry equation is going to be x equal to 0, because I grab this x coordinate, punch it in, and I get x equals 0. That x equals 0 is actually the equation for the y-axis, because along the y-axis it has the same x value, x equals 0. So when you have a vertical line, any vertical line, the equation is always x equal to a number. Okay, in the case of the y-axis, it's x equal to 0. That's also the equation of the axis of symmetry. In addition, we call this guy the base curve. Okay, because it's the simplest quadratic relation. If I look back on my standard form, I have no a value. I mean, I do. It's a equal 1. I have no b value. B is 0 and c is 0. And if I punch those values in, I get this simple quadratic equation. Okay, y equals x squared. So y equals x squared is a special case where I chop away b and c, where b and c in my standard form go away. Oops. Now we talked about the axis of symmetry. A parabola, right, has what we call a minimum y value or a maximum y value. That depends on how the parabola actually opens. So we talked about two types of openings. Okay, so one is it opens downward. So that's this way. So this is opens downward. The other one is it opens upward. Now, if it opens upward, if we look at the y-axis, we call this a minimum y value because the curve gets to about this low a y value and it only goes up from there. So this guy has a minimum. This guy, on the other hand, has the opposite. It starts off at a maximum y value and it only goes down from there. So that guy has a maximum y value. So there are a couple things that we need to go through. So if you're applying transformations, so let's say, I should back up a little bit. So we plot y equals x squared, okay? And we get this sort of curve. We get 1, 2, negative 1, negative 2. We get 1, 2, 3, 4. Okay, and the base curve's always going to be the same curve. Whoops, what did I do there? The base curve's always going to be the same curve. Okay, y equals x squared, right? So we plot that base curve, but what if I ask you to plot y equals 3x squared? We make things a little more complicated. How do we plot something like that? We plot stuff like that by using transformations. So use transformations to plot more complicated parabolas, or quadratic equations, let's say. Okay, so for example, y equals 3x squared. How do I plot something like this? Well, this guy is actually what we'd call a stretch. And that's because the value in front of the x squared is actually a 3. It means I take x squared from my base curve. These are the y values of the base curve. And it's taking all of these y values and it's multiplying by 3. This is the operation. It's taking 3 and it's multiplying to x squared. So I take all my y values, only my y values of my base curve, and I multiply by 3. You'll see graphically in a minute that that just turns into a stretch vertically by 3. So if I plot the base curve, one more time. Okay, so that is somewhat the base curve. Okay, if I plot the base curve one more time, I'd take all the y values of my base curve and I multiply by 3. Okay, so if I multiply this y value, which is 0, right, by 3, it's still 0. So I leave it. These guys have a y value of 1. So if I multiply them by 3, then I get 3. So I move the new y values up there. And I move the other y values up there. And now I get a new curve that is actually thinner than my last curve. So it's as if I've taken these handles and I've moved them up a little bit. And it causes it to be thinner. So I end up having a thinner curve. So that guy's y equals 3x squared. So that's how we apply transformations. So step 1 to applying transformations is to draw the base curve first. Step 2 is to apply the transformation and plot. Now, this type of method to plotting using transformations is only really useful if you have a few or a couple transformations. Once you start, maybe not even a few, I mean like at most 1 or 2 transformations, in my opinion. As soon as you hit maybe 3 or 4, that type of method of plotting the base curve first, then applying like a transformation one at a time is kind of a bad idea. So when we talk about the vertex form, y equals ax minus h squared plus k, when we introduce this, if you notice, the vertex form is actually littered with a bunch of transformations in it. So the transformations in detail are things like this: x squared plus k, let's say. Okay? And if k were a positive number, like let's say, example, k were 3, right? That means this is x squared plus 3. That would be a vertical shift, okay? So meaning a vertical shift this way, up or down. If k were 3, that means k were positive. That would mean up 3 units. If k were, I don't know, negative 1, that would mean it would be down 1 unit. That k is the same k here. So these transformations are actually embedded in the vertex form, right? So the vertex form is an example of when you have way too many transformations applied, and there might be a second, maybe better shortcut way of actually plotting the curve. So what about this thing? Oops. Now here I'm subtracting a letter inside x and putting a square. This is actually a horizontal shift. If h is positive here, for example, this actually means right 3 units. If h was negative 3, this would mean left 3 units. Now if h were negative 3, what that means is you have x minus negative 3 inside the brackets. 2 negatives make a positive, so that would read as x plus 3 inside the brackets. That's why x plus 3 reads as left 3. Okay? Whereas in here, h is 3, so I go x minus 3, and that's why x minus 3 is actually right 3. Okay? That h is also embedded inside the vertex form. The last bit has to do with the stretches and actually reflections. So we did an example in the homework where you had 1a out of the textbook. It was plot y equals negative 3x squared. That negative 3 is actually the a value from vertex. From vertex form, I should say. From the vertex form. This 3 itself means stretch vertically by 3, which we saw, and this negative means reflect. So in other words, when you say reflect, it actually means the curve is going to open downward. Okay? So if a is negative, and I want you to remember this, so if a is negative, okay, then it opens down. If a is negative, it opens down. If a is positive, then it opens up. Okay? So if this negative were not there, this curve would open up. But since that negative is there, the curve opens down. So what if I give you guys a quadratic relation that's super complicated? like -2 x minus 1 squared plus 1, let's say. This guy has 4 transformations. One is that it reflects. Okay. 2, vertical stretch by 2. 3, shift right 1. And 4, shift up 1. That's 4 transformations that I need to apply to the base curve. If I'm applying 4 transformations to the base curve, I probably have to draw 4 curves if I want to do it absolutely perfectly right without mistake. Drawing 4 curves can be annoying, so there must be a shortcut to plotting vertex form quadratic relations. Okay, and there is. So the rule goes, step 1, start by plotting the vertex. Now, what is the vertex here? That's the question. Well, this thing is called vertex form, and the reason why they call it vertex form is because you can read off readily the vertex of the quadratic. It's going to be h, comma, k, which we mentioned previously. So the vertex is actually going to be h, comma, k. So in our example over here, this example, the vertex is actually 1, comma, 1. So we start by plotting 1, comma, 1. So we go 1, 1. And that's going to be a vertex. Then we look up and we go, okay, this equation. How does it open? And what does that 2 actually mean? Well, the negative tells me it opens down. And that 2 we'll get to in a minute. But if it opens down, I know I have to draw a curve this way, right? So I need to know what my next few points are. And that's where the 2 comes into play. So when I plotted the base curve, I mentioned that I plot basically the same curve every single time. Now, when we first plotted the base curve, we had a table of values. But I don't want to keep doing a table of values if I know approximately what the curve is going to look like. It's going to look like this, approximately. Okay, and the curve keeps going, so I'm going to draw arrows. It's going to look like that. I want you to notice there's a step pattern. There's a pattern to these points. They're not random, right? So I move 1 to the right, and I move 1 up, and I get my second point. Since it's symmetrical, I could also move 1 left and move up 1 and get the third point. Now that's for the base curve. That's for y equals x squared. What happens when I'm given an example with an a value like this, -2? Well, that negative means I go downwards instead of up. In this example, I went up. In this example, I'm going to go down. The 2 tells me that instead of going in the y value by 1 point, like instead of going up 1, here I'm actually going to go down 2. So I go 1 right, okay, and I actually end up going down 2 units. So I go boom, that's my second point. Now since it's symmetrical, I could also go left 1 and down 2 units. So now this point, and this point are identical to these points in my transformed curve. So now how do I get my last couple of points? Well, the next part of the step pattern is I move 2 over and I move up 4 units to get to this guy. What that 2 does is it doubles the value. So I move left 2, but now I move down 8 units. Okay, so it's going to be somewhere down here. And then the other guy, I move right 2 and I move down 8 as well. So I'm going to get a curve, whoops, that looks something like this. That has a vertex of 1, 1, faces downward, has a few points listed over here, and crosses through the x-axis over here, crosses through the x-axis over there, crosses through the y-axis over there. So this guy, once more, is the graph for negative 2 x minus 1 squared plus 1, opens down, has axis of symmetry, has a maximum, I almost said minimum, has a max of y equal 1, which is the y coordinate of the vertex. What else can I say about this curve? Oh, one thing we also need to talk about is something called domain and range. Okay, so notice how I've drawn arrows here. Okay, these arrows go on forever, right? So in the horizontal, I'm covering all values of x in any parabola. Okay, so the domain is what we call the list of x values that the quadratic accepts. Now, because any quadratic goes on forever, we say the domain is all real numbers, or all values of x. That's all it means. Now, the range is list of y values. This is where things get interesting. In this case, I don't cover these y values. I don't have those, right? I don't cover anything above y equal 1, which is the y coordinate of my vertex. So what I say is the range is the values of y less than or equal to 1. I only take those y values. Y equal 1 is my absolute maximum. So what I say is the range is y less than or equal to 1. That's my range. And the domain is all values of x. So the y values might be limited, but the x values are not. And that basically is an intro to quadratic relations. And it covers standard form. It covers the vertex, the axis of symmetry, maximum or minimum, directions of opening, the notion of a parabola, base curves, transformations. Transformations only really work when you're only doing a couple of transformations. Any more than that, then it gets very, very tricky. For example, if you have a vertex form, you're doing a lot of transformations at once, potentially, then what you'd have to do is you'd have to just plot the vertex, do a step pattern based on the base curve, and then draw the transformed curve. Then we ended up talking about domain and range. This is just the list of x values. Keep in mind that the domain of a quadratic is always going to be all real numbers, meaning all values of x. It's always going to cover all of them, unless it's like a real world word problem or something like that. For example, if you've got a quadratic that has to do with time, time's not going to be negative, so you'd exclude negative values of t or x. But the range is going to always be limited by the actual maximum or minimum values. So in this case, the maximum value for y was going to be 1 based on the vertex. And so I'd say y is less than or equal to 1. What if I give you a, what if I give you a table of values? And I don't tell you if it's a linear relation, a quadratic relation, or neither, right? What do I do? So I'll give you a table of values up to about y. And then what I want you to do, this is called finite differences. Okay, it's called finite differences. To determine what kind of relation this is, what I do is I subtract adjacently these y values, only the y values. The x's don't get affected. So let's say I'm going to go 4 minus 1. That's going to be 3. 1 minus 0 is going to be 1. 0 minus 1 is going to be negative 1. 1 minus 4 is going to be negative 3. If I apply the first differences again, I get 2, 2, 2. As soon as I get a constant, meaning the same value across the column, then I say that I've identified what my relation is. So if second difference, right, if the second difference column is constant, meaning I have the same value throughout the column, then this means it's a quadratic. If first difference is constant, then it's linear. If neither, then neither. Neither linear nor quadratic. This is an intro to quadratics, and we're going to do more stuff with quadratic relations after this video. Thanks.